In the first part of our nervous system lecture, we talked about neurons and how they function. Now we're going to talk about what happens when you put neurons together to create circuits. The whole point of the nervous system is to communicate information, especially from external information, and then processing that information and sending out instructions for what to do. So if you see someone you recognize, you may interpret that information as this is a friendly person and you like them, and you will raise your hand and your eyebrows and give them a smile and a wave. Let's say this is your eyeball here, and here's your friend. Yay. You see them. This nerve from your eye is a sensory neuron. It will go to the back of your brain, which is where you identify visual information, and then it'll go into where you have your emotional center and you say, hey, I like that. And then that signal will transfer down to this location where a motor neuron comes down into your arm to raise your arm and wave. So you have a sensory neuron bring input in. In your brain, you have these things called interneurons. And then coming out, you would have your motor neurons. That is a circuit. Now, a reflex is super fast, and actually you don't need any interneurons. So if you're touching a hot surface with your finger, that signal goes up a sensory nerve and immediately comes back down a motor nerve to move your hand. So this peripheral nervous system, the peripheral nervous system is the stuff outside of your brain and spinal cord. Your brain and spinal cord are the central nervous system. That's in general where your interneurons are. Your sensory motor neurons are in the peripheral. Sensory receptors, I just wanted to point out that there are all these sensory receptors and they're all cells. They pick up certain chemicals because, for instance, here's a taste receptor. You eat things that have molecules in them, and there are little receptors on the surface of this taste-related cell. When the little compounds or chemicals touch those receptors, those protein receptors on the cell, in the cell membrane, they will send a signal that start one of these circuits. But the interesting thing is, we all have slightly different receptors here. So some people can taste those compounds and some people can't. Obviously, you don't have a clicker, so ignore this. You don't have to click in. But one example of how different cells have different protein receptors is Brussels sprouts. A lot of people really don't like how Brussels sprouts taste. There are certain chemicals in Brussels sprouts that certain people have receptors for. Other people don't. I don't have these receptors, and I think Brussels sprouts taste delicious. You may disagree, but it's not because one of us is right and one of us is wrong. It's because we just have different taste receptors, and things taste differently to us. Now, the brain, this is part of the central nervous system, and we're going to talk about these different parts of the brain. The cerebrum is this structure, like a little hat on top of everything else. It consists of 4 lobes: the frontal, temporal, parietal, and occipital, and we'll talk more about what each of those do. But the cerebrum in general it has control over higher mental processes. The other major structure you can see from the outside is the cerebellum. That controls movement, posture, balance, and then the brainstem is the really important one. This one is down at the base and central. It controls all of the basic life functions like breathing and heartbeat and blood pressure. Really important. If anything happens to that brainstem, not good. I did want to take a moment just to talk about development of the brain. At about 3 weeks after fertilization of the egg, your brain looks like this. Not too impressive. But then in another week or so, certain cells start to differentiate out, and you have these different simple structures appearing. Those continue to develop and enlarge, and I've made a rather large leap here, but you can see how these same structures have simply gotten bigger and shifted around a little bit to be the brain that you have when you're born. A lot of people try to say, well, you have a brain at 3 weeks, or you have a heart at so many days. It's really not that simple. You do have the beginning structures of these organs, but they develop over the 9-month period. And in the case of the brain, it even continues to develop till you're in your 20s. That's a long time. Okay, so back to the cerebrum. The frontal lobe is largely responsible for reasoning and judgment and planning things, logic. I do want to point out that these are all extremely simplified. They do a lot more than what I have listed here, and it's a lot more complicated, but this is a good starting point. The temporal lobe functions in sound perception, speech, and also deep down inside the temporal lobe is kind of the emotional center of the brain. It's where you attach importance to things. The parietal lobe, which is in the back and top, it has a lot to do with the signals you receive from the outside and identifying what those signals mean. And then the occipital lobe in the way back is in charge of visual processing. Sorry, not this part down here, just this part. I did want to point out the corpus callosum is this structure here. It's lighter in color because it's just a ton of axons going from the right hemisphere of the brain over to the left hemisphere of the brain, shooting signals back and forth constantly. So there's this incredible connection between the right and left hemispheres of your cerebrum. What's interesting is that each hemisphere, the right hemisphere controls the left side of the body, and the left hemisphere controls the right side of the body. Now, the two hemispheres, the right and left halves of your cerebrum, do function in different ways. The left side is more related to sequences and logical progression and verbal communication. The right side has more to do with understanding big picture and visual mental manipulation of objects. But I want to point out that if you have a corpus callosum that is functioning properly, the communication between those two halves occurs almost instantaneously. You are not a right-brained or a left-brained person. You are using both halves of your cerebrum at all times. Now, if we look at some malfunctions that occur in each of the 4 lobes of the cerebrum, we could talk about things like frontal lobotomies, which occurred in the 30s, 40s, and 50s, and even later as a treatment for psychiatric patients. This is actual picture of a frontal lobotomy in progress. This was called the ice pick method. It's a little disturbing, but the doctor would just insert a medical instrument that looked a lot like an ice pick right in through the eye and up into the forehead, and just sort of wiggle it around and mess up all the neurons in the frontal lobe. The frontal lobe was actually really important in understanding some basic neuroscience really early on. There was this guy named Phineas Gage. He was a railroad worker. He was responsible for planning a lot of things, and people liked him a lot. But one day he was using the steel rod to tamp down some nitroglycerin. It was actually very commonly done. It doesn't sound very smart, but you would put nitroglycerin into this hole and then cover that with sand and then use this steel rod to tamp down the material and then go away and then explode the nitroglycerin. Well, apparently somebody forgot to put the sand in or didn't put enough sand in, and so when Phineas Gage went to tamp this material down, it exploded, and that rod went right through his skull and right through his frontal lobe. Now, he wasn't unconscious when the doctor came. He was on the ground, but he was awake and could remember what happened and spoke consciously. He had very few physical problems besides the fact that there was a rod sticking through his head. But the rod was removed, and physically he was just about fine. The problem was that his personality changed tremendously. He couldn't plan things anymore. He wasn't really responsible. He ended up just kind of wandering around. He ended up somewhere in South America, and he couldn't hold a job, and people who liked him before said that he just started swearing and he just wasn't a nice guy anymore. He wasn't himself. This was one of the first instances where people realized that certain parts of the brain do certain things. Temporal lobe does two things. One, it's really closely associated with sound and speech, and so if you have damage, you're probably going to have some issues with something called aphasia. We're going to see a video on that.
Well, it's pliable in the other, see. You don't understand it, but it flies in the long reed comes from there, and it comes source from the country out through, see. All the underwood, see, it comes up, and finally come out here and goes out, see. You get it?
Sort of.
Yeah, if it comes out here, see, it comes out here, here, and here, and it comes in, and it comes out, and bing. That's a good fly flow, see.
That's a good what?
That's a good flow. Flow goes fly, see, it flows cold.
So that man was talking. He wasn't actually having difficulty speaking. He was having difficulty communicating. The words were jumbled. He would say real words, but they really didn't make sense. He would have words that were just made up, and it's a symptom of someone with aphasia, damage in the temporal lobe. The other interesting ation is associated with this hyperreligiosity deep in the temporal lobe. There's an emotional center. It's what says something is important, something is worth paying attention to. It's relevant in your life. If you have epilepsy, it's almost like a thunderstorm of activity. So if you have epilepsy in this really deep area of the temporal lobe, all of a sudden things become relevant to you that really shouldn't be. So if you look down and see the mouse next to your computer, you say, "Wow, that is an amazing work of engineering, and look at this pen. It's so important and carries so much emotional weight with it." Things that most of us would disregard. This can oftentimes manifest itself as someone believing themselves to be God, or someone thinking that they're talking with or experiencing some sort of extreme religious experience. The parietal lobe functions as an interpreter of sensory information. If there's damage in this lobe, usually you receive information in just fine, but your brain doesn't interpret it properly. One example of this is called hemifield neglect. The person with this condition can see, but they tend to ignore one half of the world, and it's usually the left half. These two patients who drew these pictures were asked to draw a clock or draw a flower, and you'll notice that they only drew the right half in these cases. There's a story of a woman who was losing weight in a nursing home, and her family asked what was going on, and she says, "Well, I'm hungry all the time. They don't feed me enough here." They went down to eat with her one time. She had all this food on her plate. This is her plate. That's a fork. And she only ate half of it. And they said, "Well, Grandma, if you're hungry, why don't you eat the rest of your food?" And she said, "What food?" That's when they realized that she had had some sort of stroke in her parietal lobe. And the treatment for this woman was actually just to turn the plate around until she didn't see any more food. Another interesting condition with parietal lobe damage is that sometimes you can mix up sensory locations and types. So if someone, for instance, touches you on the hand, you might think they're touching you on the back, or they might touch you on the hand and you think you smell cinnamon. So some interesting things can happen there. And then the occipital lobe. That's mostly responsible with visual information. So if you have damage there, you might lose your sight, but your eyes are perfectly functioning. You might have hallucinations. You can start seeing geometric shapes, people, really bright colors. There have been examples of people who see objects floating in the air or people walking around them. There's also an example of visual agnosia. I should have the inability to recognize objects. Let's change that. And if you're looking for an interesting book to read on some of these conditions, I would recommend The Man Who Mistook His Wife for a Hat by Oliver Sacks. It talks about a lot of issues. This one particular one, The Man Who Mistook a Wife for a Hat, he couldn't recognize his wife, and I guess whenever he saw his wife, he thought he was looking at a hat. So these things occur, and they're just simply the result of damage of certain set groups of neurons. Review here. We have a story of Mike the Headless Chicken. Around the 1930s or 40s, a farmer was cutting off the heads of some chickens for dinner, and he missed a little bit on this one. It ran away, and when he caught up to it, it was still wandering around without a head. But after a couple of days, he was still walking around. They started putting some water down his little esophagus, down the hole that was left, and putting little corn pieces in there. And he ended up becoming this sideshow attraction. So the question is, which part of the brain was Mike missing? The cerebrum, the cerebellum, or the brainstem? Clearly, if Mike is still alive, he has his brainstem intact. The other issue is that Mike was still walking around. Well, Mike has his balance and coordination, so his cerebellum was still intact. The farmer cut off the cerebrum thus making him a celebrity without a head. Fascinating.